You what?
Last class before I have to go for archaeology
Okay.
for Pokemon.
All right. So we're gonna take a couple of days to talk about counting. Okay. And maybe you're thinking like, I can count, Jason. And no, you can't. Okay. Well, it's not that you can't. It's that you forgot how.
I thought I knew clocks.
Yeah. So. So you forgot how. So before I can teach you how the computer counts, I first have to remind you how you count because you forgot. You've been doing it for so long, you forgot how it works. So if I asked you how much is a dozen, what would you say?
12.
Okay. Yeah, so you would say 12. Well, how much is 12?
In what way?
Like
How is 12 is one set of tens and two ones. That's how the elementary school teacher taught you, right?
Okay.
See, you forgot. I had to remind you.
Well, I wanted to.
Okay. So, so let's review now. Now that I've set the stage, let's review what we learned back in elementary school. So the decimal numbering system, which is the numbering system that humans use for the most part, and makes sense to us, uses 10 digits to represent all the different values. These are the 10 digits. Yeah? We have to represent every possible value using some combination of those. Okay, so how do we do it? Well, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, what happens when you need a value that's greater than 9? Yeah, you had to have another decimal place, right? So you reset that ones column back to 0, and you create a new section called the tens. And now you got a certain number of tens and a certain number of ones until you get up to 99. And then you got to reset those, and now you've got a set of hundreds. So you got hundreds, and you got tens, and you got ones, right? And we can keep going like that forever. So in decimal, each of those little decimal place slots is 10 greater than the one that came before it, right? You remembering this? So this is the important thing to remember, is that the digit itself has a base value, right? It represents a value. But the full value it represents is also about which slot it's sitting in. So like this is 1, but depending on where that 1 is, it could be representing ones, or it could be representing tens, 1 tens. Or it could be representing 100s. Yeah? And to take the idea a little bit further, we could take this value using the digits 1, 2, 3, and in a decimal numbering system, that would represent 1 hundreds, 2 tens, and 3 ones, which equals 123. All right, everybody okay? Haven't lost anybody yet? No? All right, because it's about to get a little hairy. So another kind of principle that sometimes we forget is that 0, unlike all the other digits, 0 carries no value by itself. But it can be used to tell you how that you have nothing of a certain decimal place, right? So 0 in and of itself means nothing. But 0 sitting in the thousands column means you have 0 thousands, and that is important information. And those zeros are always there. So here's that same number, 123. We don't usually draw those zeros in front of it, but that doesn't mean they're not there. right? There's an infinite string of zeros going on into really high numbers, right? That we just don't usually write out because we don't need to. We can infer that they are there. Yeah? Okay. Everybody understand that? So here we go. I'm going to teach you now two different numbering systems. Today we're going to talk about hexadecimal, and then next time we're going to talk about binary. And binary is the way the computer counts. The computer doesn't count in hexadecimal, but hexadecimal is a useful way for us to abstract binary in a way that's a little bit easier for us to understand. So, and it's a little bit easier to learn hexadecimal first and then binary than it is to learn binary first and then hexadecimal. So that's why I'm going to teach you hexadecimal first, but the goal of teaching you hexadecimal is so that when I teach you binary, it will make sense, okay? And we will work with hexadecimal in some of our projects this semester, okay? So,
Do you prefer hexadecimal or binary?
oh, hexadecimal for sure,
Why?
because it's easier. Okay, so how does hexadecimal work? Well, let's break down the word. Hex stands for 6 and dec stands for 10. So this means that if decimal is a base 10 numbering system, hexadecimal is base 16. And uses 16 digits. And here they are.
Oh,
How did the letters become
Oh, I'm glad you asked.
digits?
So that's what we're going to talk about.
Wait, don't go
So, okay.
back. The letters confused me. I forgot to finish typing.
this is also a code, right? People use hexadecimal code, like if you're like, what's the word? Like, what was the Da Vinci Code thing? What did they use? Not hieroglyphics.
Cryptex?
Cryptics, yes. Don't they use those? Don't they use hexadecimal?
I mean, I suppose they could.
I know they use this in The Martian.
Yeah.
Anyone's read that book or seen that movie?
Well, a lot of times if you're looking at machine code, most of the tools that let you look at the raw machine code will show it to you in hexadecimal. Because otherwise it would just like be impossibly long to read. And so hexadecimal kind of collapses all those binary digits into smaller chunks. Okay, so yeah.
Do people use hexadecimal to translate binary?
Oh yeah, all the time, yeah. Totally. That's what we're going to do. So, all right, so how does this work? Well, let's count to 10 in hexadecimal. You ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Hey,
10.
We call it 10.
Yeah.
that's annoying. Why
Yeah.
annoying?
That's
Brooke, you are welcome to make up your very own symbol.
In decimal, you can't have 10 ones, right?
Yeah.
Wait, why
So
not?
A becomes the 10 because it's just the one digit.
Because you stop at 9, right? Can't have 10 ones. You can only have one set of 10s and no ones.
So why don't we just call it A?
Because it's not an A. It's 10.
It just represents 10.
Yeah.
Because we can't write 10 for
Yeah.
some reason.
Yeah.
No, but it has to be one.
There's no digit for 10. This is the digit for 10 in hexadecimal.
That makes
Okay,
sense.
can we keep
but
counting?
hate
I want to
it.
know the rest of the letters.
Yeah, so we're going to go to 15 now. So 9,
Right.
10, 11,
I hate that.
12,
Yeah.
13, 14, 15.
Why couldn't we make up special numbers, like special symbols?
You are welcome to do that.
I know, but I think Mr. Hexadecimal should be shot and killed
Why are these considered ones when they're past 10?
Because it's hexadecimal, which means
Oh,
it's a
okay.
base 16.
Base of 16.
So we can go all the way up to 15 ones before we have to
Okay.
start a new spot, right?
So,
That's
oh, yeah,
the
so
advantage of it.
What is 16 then?
Oh, I'm glad you asked. So we get to 15 and we're out of digits, right?
Oh.
So what do? We open up a new slot and we start back over at 1, and now it's one set of 16s and no 1s. So the digits 1, 0 in hexadecimal represent the value of 16.
So 10 equals 16.
You know what?
No, the
One-
digits
now you tell-
the digits 1, 0 in hexadecimal equals 16.
Do you put a space? Because there's not a space in that.
Yeah, usually what you would do is you would put like a 10 followed by a little h, like a little lowercase h for hexadecimal, or sometimes people would do 0x, 0 lowercase x, and then the hexadecimal number, and that would just to tell you, hey, this is in hex. But it doesn't have to be. I just have to tell you, hey, that's a hexadecimal number. Okay, so here's another example. The digits 2, 0. Well, in decimal, that stands for 2 sets of 10s and 0 1s, which equals 20. But in hexadecimal, that stands for 2 sets of 16s and 0 1s. And so the digits 2, 0 in hexadecimal equal 32.
I'm in a riot.
Wait, can you
Yeah.
wait a second while I write this chart down?
Yeah.
Can you explain that concept one more time?
Yeah. So we've got 15 digits in hexadecimal,
Yes.
right? And which means the highest number we can encode with a single slot is 15. So once we get to 15, using that digit that we all also know as F, we're out of digits, right? Can't go any higher. So we have to reset the ones back to 0, and we start a new column. Well, the new column is 16 times bigger than the one before it. So in hexadecimal, each slot is 16 times higher than the one before it.
So 16, 32, 16. Oh,
No.
16, 40, 32, 48. I'm confused.
16, what's 16 times 16?
What?
What?
That would be 16 times higher. What's 16 times 16?
Something with volumes and stuff. 256. I was right, it does end in
I was getting
six.
close.
Okay. All right. So here's hexadecimal and decimal right next to each other, ranging from values of 1 to 30. So stare at that for a while and see. Let me know if you have any things that you want me to clarify about that.
You said this was easier than binary?
Yeah.
Awesome.
I got this.
I was rewatching Wall-E, and there's okay. What? That's how you say it.
Yes.
There's a scene where he's walking in, and there's a robot, and he's like a little secretary, and he's got 2 little fingers, and his entire keyboard is just ones and zeros, and he's like beep 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 beep.
Yep.
Us, dude. That's supposed to be us.
That's how the computers do it.
That's what it is.
Okay. So does this make sense?
Yeah.
Yeah.
Questions about this?
I guess not. Well, I did notice that, like after we go to F and we start the hexadecimals, like with the 1, 0,
Mm-hmm.
and then the 1, 1, and then it's kind of like +6 for each of those until we get to 26, and then it's 1A again, and we go back to the letters.
Well, yeah, because we're incrementing the ones column here,
Yeah.
right? So my pointer isn't there. So once you get to 16, you reset the ones to 0, and then you have one set of 16s, and then you start incrementing the ones again, and you count to 15 again with the ones. So what would be 31 in hexadecimal? What digits would you use to represent that?
1F.
Yeah.
And then 32 would be 2, 0.
Yeah.
Wait, what would 31 be? 1F?
Yeah.
Yep.
And then 32 would be 20.
Yep.
Oh wait, so the B's or the letters represent the placeholders for ones, like 0.
If they are in the ones column, yeah.
Okay.
What about like a three number, 3-digit? Like, let's add hundreds in there.
Yeah. So let's pick a number. Pick a number.
246.
Bigger number.
420.
Okay, there we go. Okay, so we have, what are our placeholders in hexadecimal? What are their values?
The A. Oh, 10.
Ones,
Ones.
Oh, placeholder.
Place
16s,
30.
No.
ones, 16s,
256.
yes, 256s. Okay, so you wanted to do a value of what?
420.
420.
Okay, so how many 256s can you get in there?
At least one.
One.
Right, yeah, one. You couldn't get two. So in hex, that would be 1. And okay, so we've how many are we left with now? We've accounted for 256 of our, what was our number again?
420.
420. How many do we have left now?
164.
164.
Yeah, I think
Okay.
so.
How many 16s can we get into that?
10.25.
Okay, so 10. So that would be, what value would we put for the 16s? A. And how many we got left now?
25. No, that's not right. Yeah, 0.25.
Just let me do the math real quick.
Because there was 0.25.
Maybe I
and
did it wrong. 420
It was
minus
10.25.
256.
So we've got
It'd be 0.5.
we've got a 256 and we've got 10 16s. How many are left?
So we've subtracted what, 200 and something?
So our number, our value we're looking for is 421, right?
420.
420. So subtract the 256,
Okay. 164.
164. Now subtract 16 10 times,
160.
160.
So 4.
Okay, so we're left with 4.
Yeah.
1A4 is, drum roll, 420.
Nice.
We did it. Okay.
That was a lot.
And can you explain how you use pcalc for hexadecimal stuff like you just did?
Oh yeah, well pcalc has decimal mode, hexadecimal mode, octal mode, octal is base 8, and binary mode. Okay? So you can do math in hexadecimal in pcalc. It's cool.
How would you do it the other way around? Like if you had a number and you wanted to know what it was in hexadecimal, how would you use it?
That's what we just did.
Well, yeah, but
Can the
you did it.
calculator do?
Is there like a button where you can put like, all right, 6,400?
Yeah, so look, if like we could just do this. Like you could say 420 in decimal mode and then switch it to hexadecimal mode and it gives you that value in hex.
Word. That makes sense, yeah.
But I don't want you to get into that habit yet because you need to understand it before you ask the calculator to do it for you.
It's like when you made us do triangles in AutoCAD, and
Mhm.
like there's actually a triangle button.
Yes.
No. Maybe you shouldn't have shown us the decimal one yet.
Okay. So how we doing so far?
No. I mean like.
Everybody okay? Have I lost anyone?
A little bit. Could you do another one?
Yeah. Let's pick another number.
Treat yourself to
6,400.
6,400?
Yeah.
Okay. How many 256s are in 6,400?
Ken was upset about it. Or in what?
6,400. That's what's the number. Okay, that's more than 16, right?
Yeah.
So we need to find another placeholder. So what's 256 times 16?
4,096.
4,096. Okay, how many 4,096s are in 6,004? So 1. You can only get one 4096 into 6004. Great. So 1. Okay. How many? So what do we have left now? So our number is 6004. We've done 4096 of those. How many do we have left?
2,304.
How many 256s can you get in 2304?
9.
9. How many do we have left now? Is it not 9, Emma?
No, sorry. The original number was 6,004.
6,400.
Oh, sorry. I thought it was 6004. 6,400. Okay, so let's go back. So what do we have left after the 4,096 then?
I think it's still
9. Wait.
6,400.
6,400 minus the 4,096.
2,304.
2,304?
Yeah.
Okay, how many 256s can you get in 2,304?
9.
9. Okay. Now what do we have left?
We made it. Did we make it?
256 times 9.
We still have so much over. What? I got lost.
Yeah.
Hold on. It should be 0. That should be it.
That's it?
I think
I
we
think
made
so.
it.
So we don't need any 1s. All right, no 1s. Should we see if we're right?
Oh,
I think it should be an extra 0, right?
yeah.
Oh, because I forgot the 16s, right?
Yeah.
So great. So it was 1900. Oh, hang on. 1900. Sorry, I forgot about the 16s. Okay, so there you go.
Are you going to ask us to do that?
Yes,
Well,
I just did ask you to do that.
more so like,
Are you gonna ask me to think, Jason?
Oh
Jason,
my
I
god,
don't
lying
want
in
to.
college? Whoa.
Jason, I don't want to learn. I'm scared.
Okay, so
Some more practice.
what's that?
Can we do like 1 more?
Yeah. Somebody pick another number.
Treat yourself to a massive number.
I've been picking the other ones, so I feel like
6,006.
Okay, bro.
we just did a
6,007?
Okay, fine. We'll do.
6, 7, 6, 7, 6, 7.
Well, can we do 1,208? 1,200.
1,208? Okay. So that's less than 4,096, so we don't have to worry about that one, right? So it's 1,200 what?
8.
1,208. So how many 256s can you get in there?
4.718.
So 4. Okay. What do we have left now?
I'm doing this in the most
Jason,
inefficient way.
question. So when we divided the 256 from the 1,208, it was like 4.7. Do you round the?
The 4 is the how many 256s you could do. The point whatever is what was left over,
Yeah.
right?
Okay.
184.
That's what we have left now. Okay.
How are you finding these numbers? Because when he says what's left, that's where I get confused.
So you've got, we just put in 4 256s. So what is that?
256 minus 4 minus the original number.
Okay.
1,024. And then
1,024. So you subtract that from the number you're trying to get,
Okay.
which was 1,208.
208.
So 1,208 minus 1,024 leaves you with
184.
184. Okay. How many 16s can you get in that?
11.
11. Okay, so what digit do we use for 11?
Uh,
B.
B.
Okay. Just making sure. Remember, 3 people have to get the same answer for it to be right. Okay. Great. So what do we have left? Now.
That's it. So
That's it?
No, is it 8?
No, wait, just kidding. I lied.
So there's 8 left?
Yeah.
Does everyone else concur?
I concur.
Yes, yes.
I need one more concurrence here before we're right.
I'm still trying to
Okay.
see what's left in there. So you did 4 times 256 to get the 1,024.
Yep.
And then we did how many 256s could fit in there, right?
So you take so once you've done that, you take that number of the 4 256s, and you subtract that from the number you're trying to get, which was
Right. So
1,204, right?
yeah.
1,208.
So 184.
Okay.
And then how many 16s?
How many 16s can you get in there?
11.
And we decided it was 11, so then you subtract 11 16s from that remainder, and what's 11 16s?
176.
Okay, so subtract that from what you've got left, and what's remaining now? Ace says 8, Emma says 8.
I,
Did a little.
8,
Yeah.
Brooke says 8. Okay, it must be right. So we got to find 8 more. Well, we're down to the ones column now, so
It's just serious,
8.
dude, okay?
You ready? Let's see if we got it right. 1,208.
Do you think they do hexadecimal in archaeology?
I don't know.
Well, computer science type of
Okay? How are we doing?
like, I think it would be easier if you physically wrote it out, I think.
I just don't understand how the 16 goes from each digit. Since there's I just don't understand how you get the 4
Okay. Well, let's look at this another way. So, we're going to do slots up here, so, well, places. We've got, so far we've got all the way up to 4 digits here. So we've got 1s, we've got 16s, we've got 256s, and we've got 4,096s, right?
okay, that makes a lot more sense.
Okay, so if I want to do a value of, let's pick another number here.
17,406.
Oh, we gotta go with it.
17,406 is the number we're trying to do. Okay, so how many, that's bigger than 4,096, right?
By at least
High.
So let me zoom in here a little bit.
I got nervous.
Okay, so how many 4,096s can we get into 17,400? So let's try it. So I'm going to say, so what I'm going to do is I'm going to say, all right, 17,406 divided by 4,096, I get 4.2951 something. So that means I can get 4,096s into there. So I'm going to put a 4 there. Okay, 4,096s. Okay, so knowing that, I'm going to say, all right, 4 times 4,096. I get 16,384. So that's how much I've accounted for by the 4,096s. So to find out what I have left, I'm going to say, all right, go back to the 17,406 and subtract the 16,384 from that. And I now have 1,022 left to figure out how to get. Okay? So, all right, well, how many 256s can I get in 1,022? Well, I take 1,022 divided by 256. 3.99. Okay, so I can get 3 of those in there. So what is 3 times 256? 768. Okay, so that, let me, hang on. There we go. Okay. All right, so we know we've got 4 4096s. All right, so 4 times 4096 is 16,384. And I've got 3 256s. So 256 times 3 gets me 768. So I'm going to add that into my memory. That's the total number I've accounted for now, 17,152. So now I got to figure out, okay, what do I have left? So 17,406 minus the 17,152. I am left with 254. How many 16s can I get into that? Divided by 16, I get 15.875. So, okay, so I can 15 16s in there. Well, so what do I put here for the 16s then? What digit do we use for 15 in hexadecimal? Mm-hmm. F. Right? That's 15s. That's 15 16s. Okay? So, great. So 15 times 16 is 240. So that's how many I've accounted for with these 16s, right? 240 worth of 16s. So great, I'm going to add that in here. So that's how much I've accounted for now. So what do I have left? 17,406 minus the 17,392 I've already accounted for. I'm left with 14 that I haven't accounted. So that means I got to do 14 ones. What digit do I use for 14? E. So the number is 43FE. Let's check our work. 43FE, 17,406.
Can you do any number?
Yes.
Yeah, that, well, yeah, 'cause you just
I think I've come around to it. I think I like it.
Me too. I just like to be grumpy sometimes.
Well, because I wasn't sure about the numbers, but now I feel like it's easier to read now that there's no double digits in the digits. You know what I mean?
In your mind, yes.
In my mind.
Yeah, it's in your mind's eye.
Yeah.
In my mind's
It's
ear.
a little bit nonsense, but I got it.
Yeah.
So the interesting thing about hexadecimal is in decimal, what takes us 5 digits to encode, in hexadecimal only takes us 4. Right? You get that same value with only 4 digits.
Why does that matter?
Well, maybe you are concerned about how much space you're taking up in your data storage on your computer.
Does one digit really make all that much of a difference? I guess over.
Yeah.
1 million.
Imagine you're trying to actually document the machine code. It would take a lot longer to do it in decimal. It would take it even longer to do it in binary. Let me see if I have this actually.
What's the question you always ask Emma about binary? I don't know, just in general, about like ones and zeros. Are you a 1 or are you a 0?
Oh yeah, which one do you like? You know, in your heart feel like you want? I feel like I'm 0. Well, I feel like I want to be 0, but I'm a 1.
I'm wondering if I have.
I think I'm the other way around. I feel
I
like
think so too.
I want to be a 1,
You're
but I'm
definitely
0.
0.
Me when I'm hashtag false.
I think Jason's a 1.
He's the guy. No idea.
I don't know, so that's just kind of like wondering.
I'm trying to have a ponder and I'm not doing well.
I don't have this on this computer. Doesn't matter. Okay. How are we doing with hexadecimal?
Can we go over the ending one more time with the last number we did? After we got the 15 point whatever number, then what did you do in the ones place?
Well, I just added all the values I'd currently accounted for and subtracted that from the 17,406, and I was left with 14.
Which is true.
That's the number of ones I have. Okay?
So you added, so you added the like 16,
Yeah.
16,384 plus 1,022 plus 768 plus 254.
I think so. Let's make sure. So 4 times 4,096 was 16,384. So we'll do, just keep track of that. And then 3 times 256 is 768. And 15 times 16 is 240. Which leaves us with 14. Okay, so to get that 14, I was just doing 17,406 minus 16,384 minus 768 minus 240, and I was left with 14, and now I know that's how many ones I need. And we do 14 using the digit, otherwise known as E. Yeah?
Oh, I see. Okay. So you don't multiply 16 each time you go up by 1. It's like 16 times 16 when you get to that 10th.
When you get to the 15th.
Yeah, okay. Yeah.
Yeah. Every time you get to this F value for 15, you're out.
Okay.
So you got to get a new spot that's 16 times more than that to start over to get new values. Yeah?
So is it just 256 times 3?
Well, in this case, because I'm saying I have 3 256s. Because I put them in the 256s column.
Okay. I see.
But you can keep going. Like, what is 16 times 4,096?
65,536.
500 what?
36.
36. There you go. So you can keep going. You can keep making those hexadecimal slots forever, and you can encode any value you want. Yeah. So if I put a 0 here, that just means I don't have any 65,536s. So I have still the same number. 043FE is still the same value as 43FE. Okay? How are we doing? Getting there? So let's do some backwards ones.
Where are we starting?
Yeah. So if I give you a value of I'm just going to make something up here. A6F. A6F. So I give you A6F, right? Now, what are our placeholders? If we've got a 3-digit hexadecimal number, what are those placeholders worth? So you've got ones, you've got 16s, and you got 256. Is just to see if that resonates with anybody differently. Okay. So let's start with the so we're doing the A stands for what? Okay, so 10 256s. The 6 stands for 16s. So I've got 6 16s, and the F stands for 15 ones. Okay, so what is 10 256s? 2,560. So, oops. So this is in hex. Now I'm going to write it out in decimal here. So this would be 2,560. It's counted for there. What are 6 16s? 6 times 16 is 96. And the F stands for 15, right? 15 ones, so 15. Great. So it's 2,560 times, or plus 96 plus 15. 2,560 plus 96 plus 15. I got 2,671, otherwise known as in hexadecimal A6F. Yeah?
Yeah.
There you go.
I just put in 15 twice instead of 96.
Yeah. So that's doing it the other way.
That was a lot easier.
You should do ACE.
I knew, dude, the best is
Yeah, what is
obviously
ACE?
I kind of don't like that E is 14, but whatever.
Okay.
Yeah.
Yeah.
So we want to do ACE. That could be a hexadecimal number. Okay. So we're going to do 10 256s. What does C stand for?
13. Wait, 10, 11, 12.
12.
Oh, I was right.
So 12 16s and 14 ones. So we know we got 14 ones. What is 12 16s?
192.
Yep, 192. What is 10 256s?
2,500.
Yep, 2,560. So what is 2,560 plus 192 plus 14? 2,766, otherwise known as ACE in hex. So we can now start calling ACE 2,766.
Oh my god, new nickname just dropped. It's way more.
Or
Please
Me
simplify
when I'm a
it.
seal.
101011001110.
Oh my god, that's what you are.
Oh, that's so cute.
That's the binary, which we haven't learned yet, but
It's like a phone number with a couple added on there.
yeah. All right. We got time. Should we talk about binary for a minute? That way, if we lose class next Monday, we might be ahead a little bit. Okay, So now let's talk about binary. Let's see how far we can get on this before I lose somebody. All right, so in this case, if we break it down, bi means 2. And so binary is a base 2 numbering system, which means you only have 2 digits, 0 and 1. You have to encode every single value using those 2 digits. Okay? So how do we do it? Well, let me just sort of like show you this first. Stare at this for a minute. Take what you've learned now about how decimal works and about how hexadecimal works. Stare at this for a minute and see if you can make sense out of it.
Does it have to do anything with odd and even numbers?
Well, kind of, because in binary, every slot is 2 times greater than the one before it.
Yeah, it's every time you run out of the.
So, I mean, odd numbers will always end with a 1, and even numbers will always end with a 0, right?
Good observation.
You just are moving the 1, and then when you run out of spaces, you add a 0, and then you add a 1, and then you add a 0, and then you add a 1.
You kick him out.
Yep. So binary is really inefficient in terms of like, compared to hexadecimal. But that is how the computer thinks, because the computer is just a bunch of transistors.
There isn't a. There's no more efficient way for us to do that? Like, are there computers that aren't made on binary?
Oh, interesting question.
I have to stop asking questions.
So the reason that computers count in binary is because the CPUs are a collection of transistors.
Right.
And transistors can have 2 states. Well, what if you could make a CPU out of some kind of material that could have more than 2 states?
Like 3 states.
Like, can you think of things that you can like make exist in more than just 2 ways?
Jello. I'm
Say
serious.
more about this.
S-
It's a state of matter.
small things that you could cram onto tiny chips.
Big
Small
Oh,
scoops of Jello.
Oh, like the little, we talked about this. Isn't it like the?
You can make atoms positive, negative,
There are
and
thousands of
neutral,
them.
right?
There you go.
That's
There are like
3.
thousands of the little microchip
Atoms,
What about like
neutrons, and electrons.
That's the.
what about like DNA?
Oh,
How many possible states are there in a DNA strand?
Oh, 3.
Oh God, I remember this.
A lot, actually.
Love that.
Right?
Flavor.
There's like the strands, and they're all like R, F, C, N, A, or
the
whatever.
like RNA.
Yeah.
I'm getting more
1 million years ago.
I'm just saying, like, there's people working on that.
Mm-hmm.
Like, how do I make computer chips out of
Biomass.
something that is, yeah.
Human
Oh, you okay?
Yeah.
Don't
Okay.
like that. AI is already bad.
Okay.
enough. Thank you.
So, like, that's the thing. There's an interesting book if you want to like read about this. It's a novel. It's a spy novel by Robert Ludlum called The Paris Option.
You have to tell me about
Yes.
It's all up in my nose.
And it's a fiction book, but it's actually like a scientist, I think at Duke University, finally gets a piece of software running on a DNA computer, and its ability to crunch data is just like ridiculous, and it kind of takes over the world. It becomes like sentient and
Exactly why we don't need to do it.
yeah. Okay, so you ready to break this down now? All right. So binary, here's what it looks like. If I take my little chart and I break it down, we got decimal, hex, and binary. So the digits 1, 0. Well, in decimal, that's 1 set of 10s and no 1s, right? So 10. In hexadecimal, that's 1 set of 16s and no 1s. So 1, 0 is 16, next decimal. In binary, it's 1 set of 2s and no 1s, which means 2. So the digits 1, 0 carry a value of 2 in binary. So in binary, each placeholder is 2 times the one before it. So we can take it up to 6 digits, and we've got 1s, 2s, 4s, 8s, 16s, and 32s. So we start with 0, and everything is zeros. And so we want to do a value of 1. We put a 1 in the 1s column. We want to do 2. Oops, we're out of digits. So we got to go back to 0 on the 1s, and we got to start a new column. And the next new column is 2s. So I got 1 set of 2s, no 1s. I want to go to 3. Oh, well, I've got some room in the 1s column, so I can add a 1 there. 2 sets of 2s and 1 set of 1s. Or like, no, sorry, 1 set of 2s and 1 set of 1s. A 2 and a 1 makes 3. Now, what if I want to, so if I want to go to 3, I say 1, 1, right? 1 set of 2s, 1 set of 1s, that's 3. I want to go to 4, oops, out of digits. So I got to reset both of those now to 0. And I bring up a new column for 4s. So now I got 1 set of 4s, no 2s, and no 1s. That's 4. I want to go to 5. I need a 4 and a 1. So that's 1 set of 4s, no sets of 2s, 1 set of 1s. I'm going to go to 6. Well, I can do that with a 4 and a 2. So I do 1, 4, 1, 2, 0, 1s. 1, 1, 0. So on and so forth. And you keep going.
Yeah, this sucks.
Yeah.
We haven't figured it out yet.
But this makes total sense to a computer.
We're not computers.
That's right. We're not computers. Okay. So let's break this down now. You ready? So let's like just build all the slots. So we've got 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s. Yeah, you keep going. So we're doing 1s, 2s, 4s, 8s, 16s, 32s, 64s, and 128s. All right. So what's the biggest number we could make here? What if I did a 1 for each of these? So this is decimal, and this is binary. So the biggest number I could make here with these digits would be a 1 in every column, right? So 1, 1, 1, 1, 1, 1, 1, 1. Okay, so I've got 128. I've got one of those. Plus, I've got a 64. Plus, I've got a 32. Plus, a 16. Plus, an 8. Plus, a 4. Plus, a 2. Plus, a 1. 255.
Hey, that number looks familiar, Jason.
It does, doesn't it?
But it's off by one.
The voices.
What is familiar about that number?
It reminds me of the hex.
It-
But it's off by 1.
It is?
Because it can't go to 16. Well, because the other one is 256. Like, in hexadecimal.
Oh, no.
Are you
I was
thinking
talking about a different thing that looks familiar about this. number.
yeah, the like network?
And to Jason's and to Brooke's.
Yeah, like that number,
I'm there.
200, well, 255 is awfully close to 256, isn't it? Right? So, and 256 is a number you see a lot in computer land
Oh,
That's a Google.
because 256s, well, what's two 256s? 512? What's four 256s?
You're asking a lot for me.
The big numbers, guys.
1,200.
1,020, 1,024?
That's what viewers want you to
Do these numbers look familiar?
Yeah,
the size of like RAM chips. They're the size of like sample buffers. They're the
The same
Celebrity numbers, if you will.
because when the computer does binary, it does it in chunks of 8 digits.
Just like in how it can take it in.
Yeah, it does it in chunks of 8. We call those bytes.
Ah,
It's a byte.
and not a bit.
No, because the bits are the digits. So a byte is 8 bits,
If you bit it 8 times,
Oh my
it's a
gosh, I remember this.
right?
I hate this. Computer scientists.
byte. What's a nibble?
A nibble is half a byte.
What?
Would that be
One digit is a byte.
That's 4 bits.
Or one is bit. One digit is a bit.
Okay? So why is it 256 though instead of 255? Because we know 255 is the biggest number you can make with 8 bits. So why do we see multiples of 256 everywhere? Because there's the 0. The 0 counts. To us, the 0 is nothing, but to the computer, the 0 is something. The 0 is a state. It is a place that the transistor is sitting. And so technically, there are 256 combinations in an 8-bit number, even though the 8-bit number can only technically count up to 255. There are 256 possible combinations.
so?
So the computer,
No space for 0
what's that?
with the 255. Like,
So it just means so if you we know that the biggest number is 111111111, right? Well, the smallest value to us would be 000000001, right? That's the smallest value that we would think of. But for the computer, the smallest value is 0000000. 0000000 is to us nothing. But to the computer, that's all the transistors set to 0, which means that is a combination. They can use that to represent something, right?
Which is why hexadecimal is useful.
Which is why hexadecimal is useful. So why is hexadecimal useful? Let me show you. Let me show you something. Anybody? Anybody?
Yes.
Okay.
You explained this 4
Okay.
years ago.
All right. All right. Just want to make sure.
I'm associating it with you at this point.
oh, okay, that's why it sounded familiar.
Let me show you something.
Well, it's the same guy.
Okay.
My dad
Jim Carrey in Living Color. Fire Marshal Bill. YouTube it. It's-
I think you did for us last time.
Okay. So digital equipment counts in binary. Humans count in decimal. Computers count in binary. And each little binary placeholder is called a bit, and 8 bits make a byte. This is just computer science jokes here, okay? Here's an example of a byte. 01010101. Yeah? 8 bits. So let's talk about bits and bytes here. Well, if a byte is 8 bits, a kilobyte is 1,000 bytes. A megabyte is 1,000 kilobytes. A gigabyte is 1,000 megabytes. Right? You see how that works? So when we talk about a gigabyte, we're actually representing the total number of zeros and ones that we can store. Okay? Now, here's where it gets really interesting, and this is why I taught you hexadecimal, is that when you're converting binary numbers to hex, you can chunk it using the nibbles. So if you split it into that byte into 2 nibbles and look at it as an independent number, we can do the first one, which is 1101, what does that equal? Well, that's one set of 1s, no 2s, one set of 4s, and one set of 8s. So 8 plus 4 plus 1, which is 13, which in hexadecimal is D, right? We can figure that out without even a calculator. And what about the other part of that, the 0011? Well, 0011 is one set of 1s and one set of 2s, which is a value of 3. So we would call this in hex D3.
Wait, can you go back? Sorry.
Sorry, hang on.
So it would be 2 sets of 8 and 2 sets of 16? It would be 1 set of 1s, 2 set of 2s?
0011 is a 2 and a 1,
Okay.
otherwise known as 3. So this is where hexadecimal comes in handy, because the computer chunks these bits in little bytes of 8. And if you want to look at, it's hard to look at the binary and understand what that means, but it's not too hard to convert that binary to hexadecimal. And in hexadecimal, you can start to pick up the patterns in hexadecimal, and it's easier for us to read hexadecimal than it is to read binary. And you guys made that observation. Going from decimal to hexadecimal is a little cumbersome, right? But going from hexadecimal to decimal, that was way easier, right? So we can use hexadecimal as a stepping stone to get us from binary to decimal in a way that's a little bit easier for us human beings to understand. Okay? So let's go back now and do some binary stuff. So let's pick a number. Pick a number, any number.
23, 20, we can do 24.
24.
24. Okay. So 24. Okay, so that is less than 32. So I know I'm going to have a 0 there, a 0 there, and a 0 there, right? So how many 16s are in 24? 1. Okay. Okay, so we've counted for 16 of our 24. So how much is left now?
8.
There's 8 left.
No, 8.
Yeah, you were right.
It's 8.
Okay. 8. 8. 8. Okay. So we're left with 8. Okay, so I got one set of 8s, and I already know I got no 4s, no 2s, no 1s. 1, 1, 0, 0, 0. Let's check our work, shall we? Binary is 1, 1, 0, 0, 0. In decimal, that's 24. Let's do another one. Pick a new number.
Yes.
1973.
Birthday, yeah.
Okay. Well, that is more than 255, isn't it?
Yeah.
So we're going to need more than 8 bits. So let's start making some more slots here until we find one that is greater than 1,973. So what would be the next one after the 128s?
256.
Yep, 256s.
And then 512.
Yep. And then 512s. Okay, we still got a ways to go here, don't we?
Sorry, y'all.
What would be the next value?
1,024.
24s.
2,048.
Yeah, then the next one would be 2,048.
Yeah. So that's bigger.
All right, so we don't need that one, right? To do 1,973, we don't need any 2,048s. Get out of here. We don't need any of you. Okay? But we can get one of the, actually, hang on. Oh, let me finish doing these. So this is 1024, and this is 2056, right? No, 2048, sorry. 2048, okay. So we don't have any of the 2048s. We got one of the 1024s. What's left after we account for the 1024? 949. Okay, well we can fit a 512 in there, can't we? So, all right, now what do we have left?
437.
We can fit a 256 in there. Now what do we got left?
181.
Oh, we can fit a 128. Na-
53.
oh,
So close.
can't fit a 64 in there, so 0 64s.
Wait. Did you say 53?
Is that right? I can't fit a 64 into 53,
Oh.
right? No 64s. I can fit a 32 into 53 though, can't I? Great. And now what am I left with?
21.
21. Ooh, I can't fit a 16 into 21. So, no 16s. I can fit an 8 into 21 though, can't I?
You can. 13.
You could.
I'm left with 13 now?
Yeah.
Okay, I can fit a 4 in there. Now what am I left?
9.
9. Fit a 2 in there. Now what am I left with? We got off somewhere.
Yeah.
We got off somewhere.
I think it's 22, is it not?
So,
Or, sorry, I was thinking about
so we got off. Let's figure out where we got off. So we're doing 1973. Oops. 1973 minus 1024. 949. Okay, we can fit a 512 in there. So minus 512. 437. I can fit a 256. So minus 256. 181. Okay, so minus 128. I can fit a 128 in there. 53. So no 64s. But I can fit a 32. So minus 32. 21. I can fit a 16 into 21, right? 5s. Okay, so I can't fit an 8 in there. I can't fit a 4 in there.
Yeah.
Actually, they couldn't work.
So I can fit a 2 in there, can't I?
Well, you can fit a 4.
I can fit a 4. Yeah, you're right. Sorry. I'm getting lost here. So I can fit a 4 in there. Sorry. Yeah. So now I'm left with 1. I can't use the 2, but I can use the 1. So yeah, that value of 1,973 in binary is going to be 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1. And a decimal, that works out to 1973. We did it!
How often are you doing this?
Not super often.
How,
Like drawing
if you were like a computer scientist, like, hello, my name is Mr. Byte, would you be doing this kind of math often?
Sometimes. Well, we're usually using the computer to do it. So, but when you're trying to figure out how to give information to the computer, if you're writing the software, sometimes you have to figure out how to give it to the computer in a way the computer can understand. So, like once upon a time, you see that little committee controller in front of you, that PV? Once upon a time, I wrote a piece of software that pretends to be that thing
Oh, how'd you do it?
by pulling in the data from it, looking at it in hexadecimal, and
translate it.
figuring out what it meant to the computer. And sometimes that involved taking it from hex to binary to understand, what do these things mean? How does the computer, how does that little thing know what the button does? And what does this binary data represent?
Were you like pressing a button and seeing what signal was being sent and then translating that signal?
Yeah. Okay. So yeah, sometimes. Turns out, and this is what we'll talk about a little bit later, is MIDI, which we use all the time, is binary.
Really? They couldn't make it hexadecimal?
Well, they did, but the computer sees it as binary. But MIDI is a binary protocol. Now, you can abstract it to hexadecimal, and it makes a lot more sense when you look at it in hexadecimal. But 100% is a binary protocol. You want to prove it? We're getting a little ahead of ourselves, but just for funsies. Okay.
I love that the symbol for the MIDI monitor app is just a MIDI cable. I think that's very fun.
Okay, so let me filter the real-time messages here. And, okay, well, let me just like, give it to me. It won't give it to me. There we go. Okay. So there's two messages. Node on, node off, right? Well, it's actually giving me some numbers here. So show me the raw hexadecimal. When I push that number, I get 3 hexadecimal digits.
I thought you were saying it was binary.
Wait, what do they mean?
Well, MIDI monitor is showing it us in hexadecimal.
What do they mean?
903C69. We'll get into what it means later.
But I want to know now.
But those are 3, those 3 hexadecimal numbers represent 3 binary bytes. Yeah?
Also,
Is
Yeah.
this 1 nibble, 2 nibble, 3 nibble?
No, 1 byte, 2 byte, 3 byte.
wouldn't it be 32?
1 nibble, 2 nibble, 3 nibble, 4 nibble, 5 nibble, 6 nibble. 6 nibbles.
And sets of 2 is
What's that?
and sets of 2 is a byte.
Yeah. So this is hexadecimal, but the hexadecimal number is representing 8 binary bits. Okay? So yeah, this thing is doing binary. We're just looking at it in hexadecimal here. Everything's doing binary. When I push a button on this thing, it sends a string of binary digits into the computer.
I got you.
Okay?
I was thinking one early, but nobody.
Now, it just so happens that 903C represents what happens when you push this key. If I hold the key down and push it some more, I get D0 and then a number. That represents aftertouch, pressure. If I move this little slider, I get B014 and then the number changes. That represents, so B014 represents this slider.
Do you think some
B015 represents this slider.
Do you think someone individually like coded each button?
Yes.
To have, okay. I'm like, okay.
You can change it.
Okay.
Like you can program the keyboard to do different numbers when you move these things.
Okay. How do you know what numbers do what? Is that
Ah, that's a later thing, yes. Okay, that's another day. But well, I don't want to, you know,
what if we don't have class on Monday?
we've already covered class from Monday. Class from Monday was binary. So
Let's get even more ahead. Let's do MIDI now.
so how are we doing on binary?
Makes sense.
Anybody any questions about binary?
So, would you just put a 1 even if there's more than one set of that number within?
Well, not necessarily. I mean, you have to start, if you're trying to do the conversion, you have to start with the largest value. Start with the largest value that you can fit,
Yeah.
right? And that'll tell you how many of these smaller values you can fit, right? Because I can fit an 8 into 1,973, but that doesn't mean I need an 8 in order to encode that value in binary, right? So you start with the highest value. So let's do another one. Let's do another one. Anyone know that reference?
2766.
Something that really cooks.
You know, I don't
I have no idea.
You sound insane.
What is it?
I am
Yes,
curious.
Jason, please explain.
Back to the Future.
Oh.
Back to the Future.
Oh, wait, say the.
Marvin Berry.
He's so disappointed.
Wait, say
Chuck, it's your cousin, Marvin Berry. You know that new sound you're looking for?
I know that. What did you say at the beginning?
Let's do another one.
Okay. I don't remember that.
Something that really cooks.
I don't remember that. Wait, who says that one?
Marvin Berry.
Same guy.
The fictional character.
And then
Okay.
I've never seen Back to the Future.
Marty's like, something that cooks. And that's when he plays Johnny B. Good.
Yeah,
Right?
It implies that he set off that. Yeah.
Yeah.
Yeah,
That in and of itself is a little edgy. But
Yeah, well, although Chuck Berry's family weighed in on that, and they're like, yeah, we're cool with that. Like, they're like, we think that's cool.
worst thing in
Yeah,
that movie.
yeah, no. It's my favorite movie.
Make out with his mom. Like 15 minutes.
Okay, so let's pick a new number.
2766. That's Ace.
Oh yeah, that's me.
Okay,
Oh.
so a decimal number of 2766. Okay, okay. What's the biggest number we can put in there? We can put a 248 in there, a 2048 in there, can't we? Okay, so what are we left with?
718.
718. Okay, so no 1024s, right? But I could fit a 512 in there, couldn't I?
Yeah. And you get 206.
We got 206 left. So, okay, I can't fit a 256 in there now, can't I? Okay, but I can fit a 128. So now what do I have left? 78. Okay, I can't fit a 64. No, I can. I can fit a 64. Okay. Now what? 14. Okay, I can't use the 32. And I can't use the 16. But I can use the 8. Now what am I left with? Okay, I can use the 4. 2. Oh, I can use the 2. And I don't need the 1s. So 1 0 1 0 1 1 0 0 1 1 1 0. Let's try it. 1 0 1 0 1 1 0 0 1 1 1 0. Decimal. 2,766.
This is
Hexadecimal?
we have to see it,
Like the hexadecimal?
just to be sure.
Well, let's figure it out.
We already did this earlier.
Did this one.
I guess we haven't gone back.
So
It just keeps happening.
2,766.
Jason, we did this like 15 minutes ago.
Well, we're going to do it again.
What's the thing you say? 30%?
Yeah.
We're gonna run it back.
All right.
30%.
All right. So I can't use any of the 65,536s. I can't use any of the 4,096s. I can use how many 256s? How many 256s could I get in 2010, which would be A, right? Okay, now what am I left with after I do 10 256s? Because what's 256 times 10? 2,560, right? So I'm left with 206. How many 16s can I get in 206? 12, so that would be C, right? So what's 12 16s? How much is that? Take that off of what's left. 192.
192.
Okay.
No, 192 is what
Oh.
12 times 16 is. Sorry. My fault.
So,
How do you get to the letter C again? Sorry.
okay. So we're looking for 2,766, right? Well,
166.
we can't fit any. What?
66, not
Oh.
76.
So we can't fit any 4,096s in that, so that's why we did a 0 on that. So, but we can fit 256 into there. How many 256s? can we fit in there? Well, let's see. So if we divide this by 256, yeah, it says I can get 10. Okay, so 10 is encoded as A. All right, great. So what is 10 times 256? 2,560. So that's how much I've accounted for. Okay, so what I'm going to do is I'm going to say, all right, so 2,766 minus the 2,560 I've already accounted for, I'm left with 206. I got to figure out how to get 206 more values here. Well, how many 16s could I use to get there? We divide this by 16, and it gives me 12 point with some, okay, great. So I can do 12, and 12 is C. Okay, so if we do 12 16s, that is 192, right? Okay, so what do I have left?
14.
Well, we're going to do 2,766, and we got to subtract the values we've already accounted for. So minus 2,560 and 192. I'm left with 14. Yeah? So what do I put here in the ones column? E, because E stands for 14 in hexadecimal. And 2,560 plus 192 plus 14 equals 2,766. So if I do, let's just check our work here. 2,766 in hexadecimal is ACE. Okay? Got it?
Wait, can you read out the binary again?
And the binary of that is 101011001110.
Thank you.
Okay.
Just getting that.
Now, in our last few minutes, because I don't want to go on to MIDI yet,
Oh, man.
can anyone figure that out?
Base 8, so.
Octal, base 8.
So. Calculator time.
I'll wait while you work on this.
OSA production starts at 3:15.
It does.
We are out of class.
But I'm off duty.
Oh, we are out of class time. Sorry.
Yeah.
Yeah, sorry.
It's fine.
So if you want to sit and figure this out, you can. If you want to have something else to do, you can go do something else.
So we still start with 1 and then go to 8.
And then 64.
And then
What's 8 times 8?
64.
64s. What's 8 times 64?
128? No.
500.
So you're working out the placeholders, right?
512.
Yeah. So you got 512, 64, 8, and 1s. So
What's the last the other digit?
I think wait.
512 times 8, right?
I gotta be careful with how I'm thinking.
4,096.
how about this? Write this number down. 5316. That is octal. Next time we meet, I want you to tell me what that is in binary, decimal, and hexadecimal.
I'll tell you that right now.
Well, we just
Without doing the stupid pcalc shortcut.
I know it. Though.
Right.
We
Yeah.
just did binary, hex, and regular decimal.
Oh yeah, that's right. Never mind.
I just
Never
I
mind.
don't
That's
need
right.
peacock, I remember.
I forgot that. That's right.
Except for binary. I'd have
So
to
figure out why this is ACE.
Okay.
That's what you're gonna do. You can work on that when we're all stuck in the snow this weekend. Figure out why that is ACE.
by design.
Okay, we're done.
Thank you, Jason.
Yep.